So welcome to Module 5, Part 2. So this is the last session of new information. Hopefully you guys are feeling a lot better about graph theory. Mark, I'm just going to mute you just for feedback, but feel free to unmute yourself to ask questions or anything. So hopefully after Part 1 you guys are feeling a lot better. I know Module 4 was very intense, so hopefully this is kind of like a nice break in so many words. So we're going to continue our discussion with graph theory by exploring Hamilton paths and circuits and looking at the traveling salesman problem, which was your discussion board. So hopefully you've kind of got an idea of what the traveling salesman problem is, especially since you had to do some research for that for the discussion board. So real quick, the traveling salesman problem, TSP abbreviated, is catchy but a bit misleading because you start to think, oh, traveling salesmen are outdated, right? We don't really have a lot of them anymore. However, it actually doesn't really have anything to do with salespeople. Instead, think of traveling salesmen as a metaphor for many different real-life applications where you have to go from different points of interest at a cost. And that cost can be time, it can be money, it can be distance, all those different ideas of cost. So the one that I like to use is like UPS. They have different locations they have to go to, and they want time is of the essence, right? So they have to minimize the time. So how do they visit each one of those places and drop off all those packages while minimizing time? So traveling salesman, I just gave you that one example. If you go to your discussion board, you're going to see a lot of different examples. Hopefully you did a lot of research and you realized some cool new ideas on how to do that. I've seen people like apply it to gaming in the past, everything like that. So today we're going to introduce Hamilton paths and circuits. So we talked about Euler paths and circuits in part 1. Today we're going to switch over to Hamilton. So here's Hamilton. He's a real looker. He's from the 1800s. So Mark, I know you were like getting down on yourself about your hair being longer, but hey, it doesn't look like this, so you're good. So a Hamilton path is going to be a path that starts at one point, ends at another, that includes each vertex. So Euler was every edge. Hamilton is going to be every vertex instead. A Hamilton circuit, same idea. You're visiting every vertex, but you're going to come back to that original vertex. So when we're talking about Hamilton, I want you to think we are not repeating edges or vertices in Hamilton. Whereas Euler, you could repeat those vertices. In Hamilton, you're not repeating edges. You're not repeating those vertices. Okay. Now, in a graph, you can have both a Hamilton circuit and a Hamilton path. I know that was different in Euler. You could only have one or the other or neither, right? You couldn't have them both. But with Hamilton, sometimes it'll only be a Hamilton path, sometimes a Hamilton circuit, sometimes both. And Hamilton circuits and paths don't have any fancy way of discovering, does this graph have a Hamilton path or circuit? You just kind of have to look and see and play around with it. So here is my first example. I'm going to go ahead and just label these real quick. Randomly assigning them F, G, H, I. Okay. So we want to give a Hamilton path and a Hamilton circuit. So I'm going to start with my Hamilton path. Boop. And you can start at any vertex. There's no restriction. You know, with Euler, you had to start with the odd vertices and end with the odd vertices. With Hamilton, we don't care. Rules are lifted. So what we're going to do is we're just going to go ahead and start. I'll start with A. Why not? And then I'm just going to visit each vertex. I kind of think of this like if you were doing a road trip and you wanted to visit all of these cities. So we just go ahead and see what city could I go to next. I could go to D or B. I'm going to pick B. And then I'm going to travel. I could go to E or C. I haven't been to either one yet. Cool. Keep going. I'm going to travel down to F. Then maybe I'll go to I. Why not? Doesn't matter. H. Maybe I'll go to G next. Then I'll hop up to E. Now, I can't go to B, C, or F because I've already visited them. So I can't repeat those vertices. So it looks like I have to end at the last vertex, D. So this would be a Hamilton path because you're visiting every vertex, every point on the graph. We are not repeating any edges. We are not repeating any vertex. So we're visiting every vertex. No repetition for edges or vertices. For both of those. So how do we switch to a Hamilton circuit? Now a Hamilton circuit is different because you want to go ahead and complete that circuit just like on a computer electronics, right? So we want to bring it back home. Basically, we go visit all these cities, but we're not going to end up in some city we don't know. We want to actually come back home. So how do we complete this circuit to get back to our original letter? Well, we could just go ahead and take this edge all the way back to A. So this would be A, B, C, F, I, H, G, E, D, and then back to A. Now, a couple things to notice. The first and last vertice will be repeated. They are the only ones that are allowed to be repeated. You cannot repeat any other vertex, only the beginning and end vertices. And something else to think about is that these are not the only Hamilton paths. These are not the only Hamilton circuits. I just gave you one example. There's actually a lot of different Hamilton paths and circuits in this graph. You just have to make sure you're visiting every vertex and you're not repeating any edges or vertices. Okay. So I like this one because it kind of looks like Pac-Man. So let's start with a Hamilton path. So Hamilton path. Now I want to go ahead and start at A. Okay, I'm just choosing a random vertex. It doesn't matter which one. Now, Mark, not to put you on the spot or anything, but do you think you could give me a Hamilton path in this graph?
No, because I'm going to get stuck at D at some point.
So you're thinking circuit, but before we get to Hamilton circuits, how about just a Hamilton path? So you're starting at one point and ending at another. So, okay, go ahead and give me a Hamilton path from A.
A, B, D, C, E.
C, E. Yes, that'll work great. Could have also gone D, E, C. That would have been fine as well. Both great options. You're not repeating any vertex. Cool. Now, Mark actually jumped into the next thing we're going to talk about, which is great that you're seeing this right off the bat. I love that. So if you're going to do a Hamilton circuit, you have to get back to that beginning point. But what's the problem, Mark? As you mentioned before.
Past D twice.
We can't repeat those vertices. So the only way to get back to A, yeah, there's edges we haven't traveled, which is great, but we'd have to repeat that vertex D. So in this graph, a Hamilton circuit is not possible because we cannot repeat vertices. And then I'll just draw in D's the problem child here. We'd have to repeat D to get back to A. There's no direct line from E back to A. And you notice even if you played around with that, there's no circuit possible. So just as a reminder, you saw here that this graph had both a Hamilton path and circuit. Cool. This one only had a Hamilton path. It didn't have a Hamilton circuit. So I just want you to notice that sometimes the graphs will have a Hamilton path. Sometimes they will have both. You just have to play around with it. There's no hard or fast rules like with Euler, right? With Euler, we were looking for the even vertices or the two odd vertices. Now, let's go ahead and look at the following graph, and we're going to concentrate just on Hamilton circuits right now. So Hamilton circuits, this is when they're coming back, connecting back home. So let's go ahead and give a Hamilton circuit from A. So do you want to give me a Hamilton circuit from A, Mark?
You can just follow the letters around. So A, C, D, E, A.
Yep, perfect. That works great. I'm happy with that. Keep it simple, right? I like to go alphabetically. So we can just go ahead and follow the letters around. Boom, we've got a Hamilton circuit. This one also would have a Hamilton path, just one less vertex that you would include. But we're not going to talk about that. We just want to concentrate on Hamilton circuits right now. It says, is there another way to write the same set of edges using the same starting vertex? Basically, we want to see, is there another way to write these using the same order? And the answer is yes, you can write them backwards. So just start from the end and write backwards, A, E, D, C, B, A. And this is actually called the mirror image, writing it backwards. Luckily, we don't actually have to write it as mirrored language. I think, didn't Leonardo da Vinci write a lot of his notes mirrored? You had to write them backwards. Anyways, sidestep. Let's get back to business here. Those are mirror images. These mirror images are considered to be different circuits, okay, different Hamilton circuits. So we're going to go ahead and illustrate that again. So we're going to find a Hamilton circuit in the following graph and write its mirror image. So I'm going to go real basic here. I'm going to start with A and just write A, C, D, B, A. Okay, cool. So what would the mirror image of that be? Just write it backwards. So A, B, D, C, A would be how you would write that backwards. Okay. Questions on that? No? Okay. It's probably very straightforward right now. Let's just keep going. So the vertex that you start with, that vertex that you start and end with, is going to be called the reference point. So you can have many different reference points, right? We could start with A, C, D, or B in this example. But rewriting the same order of edges, starting at a different vertex or a different reference point, is going to be considered the same circuit. So for example, if I had the Hamilton circuit that we had before, nothing too exciting here, A, C, D, B, A, cool. It would help if I could write correctly, DBA. Well, right now the reference point is A, right? What if we switched that and we looked at when the reference point was C? Let's change it to C. We're going to go in the same order and the same direction. We're just going to use a different reference point or starting point. So this would be C, D, B, A, and then you start back at C. So this is your new reference point. But these two Hamilton circuits are actually considered the same because they go the same direction, the same order of edges. It's just simply you're switching that reference point. And the same thing if you move that to D, B, you're going to have the same Hamilton circuit. Okay. So why do we care if we've got different Hamilton circuits or the same? Well, that's going to come into play because we're going to have to figure out all the different Hamilton circuits and be able to count how many Hamilton circuits are in a graph. So I talked about this before. With Euler, there was a quick way to know if it had an Euler path or an Euler circuit. You count the degree, right? If they're all even, there's an Euler circuit. If two are odd, there's an Euler path. However, there's no simple way to figure out if there is a Hamilton path or circuit. Instead, you have to figure it out. So you may be like, well, then what's the question? What do we want to know? Why are we studying these? Well, we're going to look at Hamilton circuits to ask, what is the shortest Hamilton circuit? And that's kind of like a twofold question where we have to talk about weighted graphs and how to figure out how many Hamilton circuits are in a graph. So let's talk about complete graphs first. This is the type of graph you're going to have to use for your homework assignment, complete graphs. So a complete graph is a graph in which every vertex is adjacent or connected to every other vertex. So just think of it as you can get from any city to any other city. These complete graphs are going to be represented using the symbol K sub n, where n is the number of vertices. So you see here, K3 would be the complete graph with 3 vertices. K4 would be the complete graph with 4 vertices. K5, 5 vertices. K6, 6 vertices. On and on and on. So let's go ahead and draw some beautiful complete graphs. I'm going to go ahead and draw K3 over here. So we have 3 vertices. Boop. And the idea is that each vertex is connected to each other vertex. Cool, it looks like a triangle. K4 has 4 vertices. 1, 2, 3, and 4. Now in this one, each vertex has to be able to travel to every other vertex. Same thing. Travel there, there, and there. And then likewise connect up on top. So it looks like a square with a X through it. But that would be the complete graph with 4 vertices. K5, if you can imagine, we're going to draw a complete graph with 5 vertices. 1, 2, 3, 4, 5. So what I like to do is I just like to start with one vertex, connect it to all the other vertices. Okay. Same thing, keep connecting it. You'll have to connect it to one less vertex every single time. But boom, we've got a lovely pentagon with a star in the middle. Cool, that's K5. Now K6 is going to have 6 vertices, and you're like, please Alicia, don't make me draw anymore. Don't worry, no one's gonna look at your drawings. It's okay. So just go ahead, connect every vertex to every other vertex. Boom. Who knew that your math class was really going to be a drawing class? It's really what it is. Math and art actually go hand in hand pretty well. Just saying. Okay. So that's my beautiful complete graph with 6 vertices. Hopefully yours looks a little better than mine. That's cool. I won't be jealous. Okay, so there is K6. The idea I want you to take away from here is that K represents a complete graph. The number to the lower right is going to represent how many vertices there are. in that complete graph. Okay, so we're going to specifically be looking at complete graphs as we move forward, and we're going to be looking at how many Hamilton circuits are in a complete graph with n vertices. So let's go ahead and try and determine how many Hamilton circuits are in K3. So, fun fact, there's only 2. It would be, remember you have to stay with the same reference point. So we're going to make A the reference point. So it would be ABCA. And then backwards, the mirror image, ACBA. That would be it. There's only 2 Hamilton circuits. Boring. But don't worry, it gets more exciting. What about in K4? There's a lot more. So here I have a table, but we're just going to go ahead and look at this first column. So this is if your reference point is A. Okay. If your reference point or your starting point is A, there are going to be 6 Hamilton circuits. Boop-a-doop-a-doop, 6. And here's the list of all of them. Luckily, we don't have to figure that out. We've got it. We're good. And you'll see that it's the one direction and then mirror image. And you can look through those and kind of explore it a little bit more. Now, the number of Hamilton circuits in a complete graph with n vertices is going to be found using the following formula. N minus 1 factorial. It's supposed to be a factorial. So as a reminder, that exclamation point is that countdown, right? 5 times 4 times 3 times 2 times 1. We used way back in week 2. It's a good time to review since our final exam is next week. Speaking of which, I just posted the notes and I did look at some of the questions and I made them a little bit easier. So you don't have to like do modular exponentiation in your final. So good news. So anyways, let's go ahead and find the number of Hamilton circuits in K7 and K15. I should note that n is the number of vertices as a reminder. So the number of Hamilton circuits in K7 would be n minus 1, so n is 7. 7 minus 1 factorial. So it would be 6 factorial, or I think it's 5040. Oh, nope, 720. Just kidding. I actually teach this in another class too, and that was the answer to their homework. So number of Hamilton circuits in K15. What did we find for that? 15 minus 1 factorial. This is probably going to be the easiest calculation you've ever done in your life, right? 14 factorial. Now, if we do 14 factorial, it's going to give us a huge number. It's like 8.7. Wow. That did not like me. 8.71782 times 10 to the 10th power, which is just basically moving that decimal 10 spots to the right. Essentially, it's like 8 billion, I think. I think that was what we found. So we're just going to end with 14 exclamation point, okay? So luckily, you are not going to have to list out all of the Hamilton circuits in K15. You're welcome. Instead, what we're going to do is we're going to be looking at how to calculate them and then looking at a couple different methods. So live classroom question. So I'm doing real basic. I obviously ran out of questions, but this one is, what is your favorite food? And I'd have to go with pizza and sushi. Not together. That sounds terrible. Basically, any Italian food, any bread, carb. Yep, I'll take that. That sounds delicious. Okay, so just go ahead and enter what is your favorite food, and then we can continue on. So, as I mentioned before, we're going to be working with complete graphs and we're going to be working with weighted graphs together. So, weighted graphs are the next components we're building on here. Weighted graph is a graph in which each edge is assigned a weight or a cost. The weight of an edge is the cost to travel that edge. So if we look at the edge AB, the cost would be how much it costs to travel. So if we look at this graph, here's Willie, he's our traveling salesman, and we're looking at how much it would cost for him to go from city A to city B, and it looks like $185. So the weight would be $185. How about EB? What would be the cost to travel EB? Here's E, and then going to B. Boop, it looks like 200. Boop. Cool. Awesome. You're like, where does the hard part come in? So now we're going to kind of get into the traveling salesman problem idea. So here is a graph again, Willie, with our traveling salesman problem. It has 5 vertices. It's actually a complete graph. It's not in the same shape as the other one, but it is a complete graph with 5 vertices. So it would be K5. It says find a Hamilton path that starts at A and ends at D. So start at A and end at D. So remember, with Hamilton paths, you're starting and ending at different vertices. Circuits is when you come back to the start. So it doesn't really matter. We're just going to randomly assign. So maybe we're going to go from A to B. I like to go in alphabetical order. So let's go to C next. And then we can't go to D because we actually have to end at D. So I'm going to travel to E first. And then I'll end at D. Okay, cool. Now we need to give its total weight. So we just need to take those values and add them together. So weight will be 185 plus 121 plus 120 plus 199. Did I get the weight of all the edges? Looks like it. So add those together and you get 625. Okay, so the total cost to make this trip would be 625. So instead, we want to go ahead and find a Hamilton circuit that starts with edge CD. Let's actually say that starts with vertex C. I like this better. Change that to vertex C and give its weight. So let's actually go C to D. And then you could go to A, you could go to B, you could go to E. I'm going to go ahead and travel to E because I feel like it. So C, D, E. And then let's see, let's go to A. And then let's go over to B. Now it is a circuit, so that means we have to end where we started. Boop. So we're going to start at C. With complete graphs, they always have a Hamilton circuit, several Hamilton circuits, so just a heads up. And then total weight, we need to go ahead and add those all together again. So let's see, we have 174, 199, 133, 185, 121. I think I got everything. 5 edges, so that's correct. 174. Okay, so the total weight of this trip would be $812. So So are you guys super sad that there isn't super complicated math today? You're like, where's the hard math? It doesn't get more difficult than this, really. The calculations are pretty simple today, so that's a good thing, right? Yay! I'm going to go ahead and just skip over this last problem. I don't like it. We're not going to use it. It doesn't matter. I know why I put it in there, but we're not going to use it, so don't worry about it. Okay, so any questions about the weighted graph or the Hamilton circuits for right now? Are you okay?
I don't.
Okay, cool. Okay, so notice that some circuits are lower cost than other circuits. So depending on which trip you take, right, 119 is cheaper than 185. Some of these trips are going to be less cost. So they're going to be considered optimal. So the lowest cost circuit is referred to as the optimal circuit. And that's really what we're trying to get to with the traveling salesman problem, is we're trying to figure out what is the optimal circuit. So when we're talking about traveling salesman problem, sites are the vertices, costs are the weights of the edges. A tour is a Hamilton circuit, visiting every vertex and coming back home. And the optimal tour is the lowest cost Hamilton circuit. So the question is, how do we find the lowest cost Hamilton circuit? Now, the basic answer that most people would give, well, find all the Hamilton circuits, calculate them all, and then choose the lowest cost, right? Yeah? But do you remember back when we were trying to figure out how many Hamilton circuits are in a graph? And we said, if you have 15 vertices, which isn't that many, right? 15 cities that you have to visit. And you were to figure out how many Hamilton circuits were in there. It was like 8 billion. I don't know about you, but I don't want to have to go ahead and find 8 billion Hamilton circuits, calculate them all, and then find the lowest cost. Now, if you have a computer, the computer can do it for you, right? However, that's still going to take a lot of time. What if you have 200 vertices or 200 cities that you have to visit? Are you going to find 199 factorial? That is a huge number. You're not going to do it, right? And even with a computer, it can take forever. That's why if you research traveling salesman problem, you might have seen that they're always looking for a better algorithm on how to come up with that optimal solution and guarantee an optimal solution. So there's like money awards for people who come up with an optimal solution. Now, there's many different algorithms out there on how to come up with the optimal solution, but here are 4 that are discussed in your book: the brute force method, nearest neighbor, repetitive nearest neighbor, and cheapest link algorithm. We're only going to talk about the first 2. The third one isn't really hard at all, but we're just going to talk about the first 2 for right now. So TSP method number 1, brute force. So brute force, if I think of brute force, I think of like you're just powering through, like to get through that door, you're just going to slam your body through the door, right? So that's kind of what I think of when I think of doing the brute force method. Basically, you're just going to power out all of the possible Hamilton circuits. Then you're going to calculate each of their weight. And then you're going to go ahead and say which one has the least cost, and that's going to be your optimal tour. Cool. So, another thing that you need to keep in mind with the brute force method is that it will always guarantee the optimal solution, because you're always going to come up with the cheapest because you've looked at all of them. You know which one is cheapest, right? So you will always be guaranteed the optimal solution for brute force. However, it's highly inefficient because you have to check every single Hamilton circuit, calculate every single Hamilton circuit. That's a lot of work. So we don't generally do the brute force method. In reality, we use some of the other methods. And I could go on and on about order and time and all that fun jazz, but we're on a time limit. So let's go ahead and actually see how to calculate or how to do the brute force method. The first thing we want to do is we want to remind ourselves how many circuits you'd have to check if you were to do the brute force method. Now, recall that the number of Hamilton circuits in a complete graph is n minus 1 factorial. So number of Hamilton circuits in K5 would be 5 minus 1 factorial, or 4 factorial, which is 24. I don't know why I need to do that on my calculator. That's okay. 24 circuits. But half of those are going to be mirror images. Now, if you think about mirror images, they're the same set of edges, you're just going backwards. So they're going to create the same cost, whether you go forwards or backwards, right? Same cost. So we don't need to replicate that. So we can actually divide out the mirror images. And to do that, we're simply going to take that number and divide it by 2. So we would only need to check 12 circuits in a Hamilton, in a complete graph of 5 vertices. We'd only need to check 12, which you're like, cool. The less we have to check, the less we have to come up with. Always a good thing. I already kind of mentioned that, but again, since the mirror images have the same weight, just go in the opposite direction. We divide this number by 2. That's what I already said. I got ahead of myself here. So what is the optimal torr? Now, I went ahead and just pasted all 12 Hamilton circuits and their mirror images, and then all of their costs. Cool, I did that for you. Yay. I didn't actually do this. This is from a book. But it's to give you an idea of how this is going to look. You're going to write out the Hamilton circuit. You're going to write out the mirror image. You're going to calculate the total cost. And then you're going to say, who had the lowest cost? Right here. That would mean that A, D, B, C, E, A, or the mirror image, A, E, C, B, D, A, are the optimal torrs. Okay, so that would be our conclusion. Those two Hamilton circuits would be the optimal torrs. Okay, so we're going to do this together. We're going to do the brute force method on the following graph to find the optimal Hamilton circuit. So right now I want you to notice that there are 4 vertices, and this is a complete graph. Everything is attached to everything else. So this would be K4, the complete graph with K4. So the number of Hamilton circuits would be 4 minus 1 factorial. Take the number of vertices minus 1. So this is 3 factorial or 6. Now, the number to check is half of that. So we're just going to take 6 divided by 2, which gives us 3 circuits that we have to check. Cool. Yay! So what I'm going to do is I'm going to create a little table here. So I'm going to have my Hamilton circuit. Boop. And then I'm going to have the cost. And then I'm going to have the mirror image. Boop. Okay. Boop. Okay. So I'm going to start with the most basic one. Okay. A, B, C, D. Cool. It's probably the one that you were thinking of too, hopefully. A, B, C, D. And then, of course, we have to go back to the start. Now, the cost, we're going to add together those edges. So 10 plus 14 plus 7 plus 12 is 43. Now I'm going to write the mirror image. Remember, the mirror image is just this written backwards. AD, CBA. So we can't come up with those anymore. So we need to come up with another Hamilton circuit. So the best way that I like to think of this is going in a different direction than maybe you went before. So if we go down to D, well, we've already went that way before. Doesn't mean we can't again. But for right now, I'm going to actually go to C. I haven't gone that directions yet. There's no A to C right now. Okay. Now I'm going to go up to B. Why not? Now I can't go back to A because I have to visit D first. And then I'm going to end at A. The one thing I want you to notice is that different Hamilton circuits will create different shapes on your item. So you'll see that the purple was a square and the green is kind of like a X. Oh my God, I forgot what it's called. It'll come to me later. You know, like the little sand... The timer, like a little sand timer. Okay, anyways. Just go ahead and add those links together. 8 plus 14 plus 10 plus 12. It looks like the total cost is 44. Already we're seeing that's more than the other one, but that doesn't mean that this one's optimal. Let's go ahead and write the mirror image. AD, BCA. Now, there's one more left. This might be harder to see. So I'm going to go ahead and just show you what it is. So it's A, B, D, C, A. A, B, D, C, A. And if you look, there's no other one that has A, B, D, C, A. It's essentially all the permutations of these 4 letters. So if you want to tie it back to that probability week that we discussed, we're really looking at how many different ways can you change the letters or permute the letters here. So again, let's go ahead and add that together. 10 plus 8, 10 plus 8 plus 10 plus 7. 35. Again, let's go backwards. A, C, D, B, A. So what does that mean? What would the optimal tour be? The optimal tour would be A, B, D, C, A or A, C, D, B, A. Boop. And the reasoning is because it costs the least. So again, brute force always guarantees an optimal tour, but it's the most inefficient. It's going to take the longest amount of time because you have to find all those Hamilton circuits and calculate all of the cost. It's a lot. Any questions on brute force method?
No, I understand that one.
Okay, cool. The good news is that on your homework, you'll have a complete graph of 5 vertices. So if you look here, they kind of already give you what those 12 Hamilton circuits will be. So you can kind of use this as a cheat sheet to help you out when you're doing the brute force on your homework. Okay, so the second method that we're going to talk about and end with is called the nearest neighbor algorithm. So as you might think, nearest neighbor, we're going to want to go to the neighbor that's the closest, right? If you're looking there. So brute force algorithm takes too long. Too long. It's inefficient. If you start getting beyond like 5, 6 vertices, it's way too time consuming. So we need a faster way to come up with a good answer. So as a reminder, you need to visit every vertex once, and you cannot repeat a vertex for Hamilton circuit. We already know that. So what you're going to do is you're going to start from your home city, okay, your reference starting point. Then you're going to go to the cheapest city. So we're going to hop over to the cheapest city, and then we're going to look from there and say, okay, what's the next cheapest city? Let's go there. And then we're going to continue on. The only restriction is you can't come back to a vertex you already visited until you visit all of the vertices and you come back home. So we're going to go ahead and use the nearest neighbor algorithm on our traveling salesman guy, Willie. So we're going to start at A. Now, as I look here, I need to pick the cheapest neighbor to visit. So B is 185, C is 119, D is 152, and E is 133. So it looks like I'm going to travel to C, and I'm just going to write down the cost as I go. Okay, so where should we travel to next? We have B, D, and E that we could travel to. B is 121, D is 174, and E is 120. Looks like E is going to be the cheapest. So 120. So we have B and D left. So where do we think we're going to go? B is 200, D is 199. So I'm going to go ahead and take that dollar cheaper option. Go 199. Now we don't have any option. We have to go to B next because that's the last vertex we have to visit. Oops, that's DB, excuse me. And then we have to come back home. So we have to take that edge. So that would be 150 plus 185, which is going to give you a total cost of
73.
how much?
773.
Yes, 773. Now, you might be like, hey, that's a decent cost. It's easy to do, right? It was fairly quick compared to the brute force method. But if we go back to the brute force method of this example, you'll see that that's not the optimal torr. The optimal torr has a weight of 676. Ours was 773, right? So there's a disconnect there. Even though this is quite a bit faster, right? Quite a bit faster. It does not always give us the optimal answer. So we say that it's efficient, aka fast, but approximate. Does not always guarantee the optimal. Sometimes you'll get lucky and you'll get the optimal torr, but not always. Not always. So nearest neighbor, sometimes you'll get the optimal, sometimes not. So let's go ahead and use the nearest neighbor algorithm to find the Hamilton circuit starting at A. So where would you go next with A? B, because it has a cost of 1. So that sounds awesome. And then where would you go next? D? D has a cost of 2. And then where do we have to go next?
C.
We have to go to C. And then we have to go back home, which is B. Oh, I'm sorry, A. What? You're like, why are we going to B again? Okay, so that looks like 13. Okay. Now, we're going to see if it makes a difference which vertex you start with. What's your reference point? So let's go ahead and start with B instead and see if it makes a difference. So if I look here, I'll want to go ahead and go to A next, right? That's the cheapest. So you're like, okay, well, we're still going to A. Cool. But now, should we go to C or D? Looks like we should go to D, right? So that's going to be 3. And then we have to go to C, because that's the last place we need to go to. And then we need to go back home. So this is actually 15. Well, if we look at this, which one would we rather pick? We rather pick the first one because it's cheaper. Does that mean that this one is the optimal solution? Not necessarily. We haven't done the brute force method, so we don't know for sure. But repeating this nearest neighbor algorithm, which kind of leads into the repetitive nearest neighbor algorithm, which is the next one, is basically repeating the nearest neighbor and then just seeing which one is the cheapest. It's quite a bit less time consuming to do that. So I just like this Donald Duck right now. Let's go ahead and hop on over to our classroom. We are in module 5. Fun fact, remember that next week we only have one live classroom. It'll be on Tuesday at 1, so I hope you can make it. It's going to be the final exam review, so it's a great time to ask questions. If you look here, everything's on the calendar. The class does end next Friday, so June 19th. Can you believe this class is almost over? Whew, went by so fast. So next week you'll see that you're in blue in case you're wondering. We have the discussion board and your last live classroom, and then everything ends on the 19th. Final exam, live classroom, and reply post. So let's just talk about module 5 a little bit more. Make sure you've got enough detail on that discussion board. Double check the rubric to make sure you have enough. A lot of you are doing great with the elaboration. I feel like I can't talk today. It's a real problem. Okay, so module 5 assignment. Now, to emphasize something, I really want to emphasize this. In number 1, you have to create a weighted complete graph with 5 vertices. So all of your vertices have to be connected to one another. And you have to label all of your points, and the distance has to be accurate, and in the sense accurate to one decimal place. So like 5.1 miles, 6.9 miles, so on and so forth. Okay, so try to be accurate when you're creating that graph. Did you have any questions on the graph, drawing the graph or anything?
No, you showed us how to make the dots last time. That was cool.
Okay, cool. Hopefully that's fun. I enjoy drawing on Word. So using the graph in part 1, make sure that you talk about if there's an Euler path. So be careful on number 2. I see a lot of confusion with this sometimes. Euler, remember you're visiting every edge. Euler is E for edge. Okay. But for number 3, this is where you're going to start using the process we just talked about. 3, it says, using that graph, find the optimal tour for your graph by applying the brute force algorithm. So I want you to go ahead and show all of your work. The best way to do this, in my opinion, is to go ahead and insert a table. I didn't give you enough, but just go ahead and just be like your Hamilton circuit, your cost, and then your mirror image. And just make sure you have a little conclusion with the optimal tour is blah, 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 blah. This one's a little bit more time consuming, but you kind of get the idea there. Number 4, what you're going to do is you're going to find the Hamilton circuit by applying the nearest neighbor algorithm with the following reference vertices. So in A, I want you to use your place of residence as the reference vertex. So your place of residence, your home, essentially. And you're going to go from your residence and you're going to pick the cheapest link. And then in part B, you're going to pick your restaurant. So apparently you live at your restaurant now. And even though nobody's allowed to go outside, you live at your restaurant now. And you can go ahead and do the nearest neighbor algorithm. And it's interesting to see if you get two different results, if you get the same, what happens. But the last question is, are either of these Hamilton circuits considered optimal? How do you know it's optimal? You have to justify your answer. Hint, hint, check question number 3 as kind of a help on number 4. Wink. So each of your assignments will look very different. But just make sure to answer the questions completely, justify your answer all of the different parts. On number 2, I do want to emphasize real quick, make sure that you're telling me if there's an Euler path or Euler circuit and why, and then also provide an example of either the Euler path or Euler circuit in the graph given. Okay. Any questions on the homework at all? Okay, cool beans. And then quiz 5, just as a reminder, I did put up the practice quiz on the course announcement, so definitely check that out before you jump into the quiz. This is your last quiz before the final, so you want to score the highest possible. Definitely take your time to go through that practice quiz. And you can always email me questions on the practice quiz or the live classroom notes practice problems. So keep that in mind. And if you have any questions on the homework at all throughout the weekend, feel free to email me for clarification, or if you want me to check something, feel free as well. So that is all I have for today. Week 5, all the new information is done. Now you just got to go apply it. Okay. Thank you so much for coming, and hopefully I will see you next Tuesday.
Tuesdays are hard.
Oh.
Thursdays are the only better out of it. So I know the next Tuesday is the last pass, so we'll see. I do have a link I wanted to share with you that I found for the discussion.
Oh yeah. Okay, let me go ahead and stop the video, and then we'll go ahead and look at it.